All right, today we're going to take a look at, what are you laughing at? We're going to take a look at hydrolysis reactions in this case. All right, and let me point one thing out. I just have a quick question. One of the things that we said is we said that when it came to substances, they're going to fall in the category of being acidic, basic, or neutral. Now, if we take a look at something such as maybe this here, HF, AQ, and say I was to introduce it into water, would this end up producing something that's going to be acidic or basic?
Acidic.
Acidic. Oh, with great confidence, because that H plus is going to go over here. We'll get something like H3O plus right here. If we had something like NaOH right here, and if I placed it in water, would I have something acidic or basic? Basic, because I get the hydroxide that kind of pops off in this case. Now, one of the things that we need to take a look at today is what if I give you something like this? NaCl or NaF. It doesn't have, in this case, a hydrogen cation. It doesn't have the hydroxide in it. And if you look at it, that is a metal, that is a non-metal, so therefore it's what sort of substance? It's a salt. And that's what we're going to take a look at today. We're going to see if we take a salt and introduce it in the water, will it cause, in this case, the solution to be neutral, basic, or acidic? And in order to do this, we're going to have to kind of break this salt into two pieces. We're going to have to look at its cation component and see how it's going to interact with water. And we'll also look at the anion component and see how it's going to look in water as well. So let's kind of just jump into this. And you're going to see it in the notes, but what I like to do is I like to not even look at the notes. I want to kind of see if we can figure this thing out for ourselves here. And then we'll go to the notes, and it's going to say the exact same thing. If I take something such as the following, say I take Na positive. And once again, I'm working with NaCl here. So I'm going to break it into two pieces. I'm going to say, okay, you know what? That NaCl, what a terrible aqueous, I can do better here, AQ. I want to just study how it's going to interact with water in this case. And if I look at it, I know what water is. You kind of say, hey, when we think about water, you should think of it being H plus and OH minus in this case. Which means that what's going to end up happen here is we're going to have this sodium take on the H plus of the hydroxide. The hydroxide. So I'm going to get NaOH, which means that I'm going to have plus, in this case, H plus out here. All right. And if you look at it, one of the things that I can see is I can see that this could not be. What I have written up here is it's not going to happen. And the reason why I know it's not going to happen, and watch closely. And also, one of the things, didn't we just talk about a second ago that, hey, I can always kind of check to make sure I did it correctly because the charges on both sides are going to match up. Hey, +1 net on this side, +1 on that one. So I know I did this thing correctly. This equilibrium that we're looking at here says I can exist so long as this thing can exist as a unit. Well, one of the things that I know is that can't exist because sodium hydroxide will completely dissociate. It cannot exist as a unit that I have shown here, which means that I won't get this. And if I don't get that, then hey, this hydrogen cation will never separate from the actual water in this case. So one of the things that we're going to see in a second is that if we get a strong base on the product side, then I know that the way that it's shown cannot be correct. I'm going to go in here, I'm going to do the following. Put a line through it, I'm going to say no reaction, which means that all I got is a sodium cation in the water, and I got water. And because it's not getting any H plus or hydroxide, I can say this thing is just going to lead me to something that's going to be neutral. So from the cation's perspective, it's like, hey, I'm neutral here. I'm not doing anything. But at the same time, if we go to the chloride, let's see what's going to happen here. If I take chloride and I look at its interaction in this case with water, H2O liquid. And I go down here and I kind of do this equilibrium thing here. I'm going to go HCl aqueous, because once again, I know that the H plus is going to be the thing that's going to come down here to that minus. And then I'm also, hey, the other component of the water that's left over is the hydroxide. So I got to figure out whether or not this can exist. And if I think about HCl, HCl is a strong acid. You will never ever find HCl together like this. The hydrogen cation, the chloride will be separated because it's 100%, once again, going to dissociate. So that is wrong from the picture here to show it as actually being a unit. So I'm going to go in here and say, yeah, no reaction as well. Which means that all I got is I got chloride and I got water. Hey, I'm just going to go with neutral. I got chloride floating in water. Not changing. pH is still pH of 7 in this case. Now, I'm going to change this up a little bit. Instead of sodium chloride, I'm going to go with something like sodium fluoride. So I'm going to kind of show you what's going to happen here. Matter of fact, well, we'll leave it up there. This is not going to change. I'm always going to check my cation out and say, okay, sodium, you're going to interact with water, you get sodium hydroxide, I'm going to get the H+, you're a strong base, you can never exist, as seen right here, no reaction. Watch what's going to happen here now. I'm going to go in here, and instead of chloride, I'm going to go with fluoride right here. I'm going to get HF aqueous plus I'm going to get OH minus aqueous. And if you look at it, what I can see here is this. Is this a strong acid? No, it's a weak acid. And when we think about weak acids, they're like, hey, we dissociate to a certain degree, but we also can exist just like this right here, which means this is acceptable. And I can see that, hey, if this thing can exist, then I'm gonna have some hydroxide here, and that's gonna give me a net effect of being a basic solution is what we got here. So when I look at it, I'm gonna say, hey, the sodium cation, it's causing things to be neutral. But if I look at the fluoride, when it goes through this process, it's going to end up causing this part to be basic, which means overall, the solution is just basic. Because if I have basic and neutral, it's going to be basic in this case. Yes? Absolutely. So what we're actually looking at is whenever we see this sort of reaction playing out, where the ion can produce something that's either going to be basic or acidic. This is known as hydrolysis. Hey, look at that hydrolysis reaction. A cation anion is able to produce and cause a solution to be basic or acidic. And we're going to look at a few of these. And don't worry, I got about 5 more of these that we'll kind of run our way through and kind of figure out what's going on when we add this actual song. Matter of fact, let's do this one really quickly. What if I gave you this one right here? Now, sodium hypochlorite is actually your household bleach. Inside of your bleach, you can go home tonight and take a look at it. And it's going to have on the ingredients, it says sodium hypochlorite. And it's inside of water. So it's just like they put some inside of water. The question I have for you is I want you to start all the way back at the beginning. I'm erasing all this. You know what? Instead of sodium, I'm going to change it up for you. That way you can't just copy the first part. I'm going to go with lithium hypochlorite. You could put that in bleach as well. That's fine. It would do the exact same thing. I'm going to talk about bleach right after this. So see if you can write. Once again, start off with the lithium. See what sort of interaction it's going to have with water. See if you can get that product to exist. And remember, the rule of thumb, if it's a strong acid, a strong base, yeah, okay, it's not going to happen. If it's a weak acid or a weak base, then yeah, it's fine. All right, so everybody finished? All right, so if we look at lithium and its interaction with water, will there a hydrolysis reaction playing out? No. So we'll go here and we'll just simply say lithium, cation, aqueous. Man, these aqueous are getting worse and worse. There we go, aqueous. Plus H2O as a liquid, and once again, it's got to go in this equilibrium. I'll get lithium hydroxide. Well, I know, once again, alkaline-containing compounds are always going to be 100% associated. So it will not exist as this unit here, and therefore I am not going to get the H plus kind of coming out of this thing. So I'm going to say, hey, no RXN. And once again, these two things mixed together with inside the beaker is still just going to be neutral here. But if I go with the hypochlorite in this case, and I have it try to interact with water, is the hydrolysis reaction going to play out? Yes, because it is not one of the 7 strong acids. If it was one of the 7 strong acids, I'm going to be like, no. But in this case, it's not. So what I can look at here is I can say, absolutely, this is going to be basic. That's what I'm getting here. Because I see, once again, the hydroxide coming out, so I got a basic solution. And once again, overall, I'll even write here, overall, the solution is basic. Got you. Now, the only reason I kind of put this one up there, once again, bleach has sodium hypochlorite in it. Has anybody ever got bleach on your hands? No? All right, don't do it then. I'm just going to say I have, because, dude, young ladies wash clothes? Hey, man, you must be just so, I mean, I've got a little bit on my hand. But the only reason I was asking, because if you did ever get it on your hands, one of the things you would notice is that bleach is kind of slippery. And if you remember, I told you things such as soap. Soap is a base. Bleach is a base. And one of the things I always told you I would do sometimes, if there was some liquid that was on the countertop and I wasn't sure if it's water or some sort of base, I always just kind of rub it. If it's slippery, it's a base. If it's not, then I know it's not a base in this case. So just kind of point that out. All right, here we go. What we are going to do is look at one more problem here. And then we'll go right into the notes, and the notes are going to kind of show the exact same thing that we just went over. What if we had something such as ammonium? Ooh, this is a good one. Fluoride. That's a good one. So you gotta think about, we got the ammonium cation and we got the fluoride. So take the ammonium and see what its interaction is gonna look like here. And by doing that, I can pull up something. And let's take a look at it. So I got one value really quickly. You need this. There you go. Such a good problem. All right, so if we look at it, let's see what's going on here. First of all, I'm going to start off in this case with the following. So we go NH4 positive aqueous. That's going to interact with H2O. So once again, if you're ever confused as far as what is going to go with this, just think of water as H plus and OH minus. I know that anion is what's going to kind of group up with this thing right here. So if I look at it, what I'm going to get is kind of an equilibrium that looks like this here. I'm going to get NH, I just lost my train of thought there, NH, and in actuality, I am sorry, this one's different. Oh, it's actually going to be this right here. And this one we gotta make sure we talk about. Did anybody get this first of all? Or do you kind of do it differently in this case? No? Okay, one of the things, which is okay. What I want to point out, wait. What did I just do there? Come on, Mr. Hurlson, that's wrong. That looks better. But it'd be H3O plus. There we go. Because what's going to end up happening is this is actually my acid here. So that H plus is going to donate itself onto, in this case, the water. So I'm going to end up getting my hydronium cation, and I'm also going to get my ammonia. Now, if I look at it, one of the things I got to look at is I got to figure out what in the world is this thing right here. But if I look at it, if this is going in the reverse direction, would this be an acid or a base? It's a base, because we would call that thing like our conjugate base, right? When it comes to the actual bases, if you remember, the only strong bases we have hydroxides in them. Remember we had the rule that said, hey, the alkali metals and hydroxides, strong bases. We had CBS, and remember, CBS, calcium, strontium, barium. If they're with hydroxide, strong bases. Everybody else is classified as a weak base. So I'm done. I know you have to be a weak base in this case. So this hydrolysis reaction can absolutely play out in this case. Which means that when I look at it, I got H plus down here, which means that this thing has to be acidic. So I see that as being acidic here. If I go and I look at the actual fluoride here, which is one that we've already looked at, we go in plus H2O as a liquid. It's going to go in and produce HF, aqueous. Plus, we're going to end up getting this case now. We got here OH minus aqueous. And clearly, for this hydrolysis reaction, we're going to be in agreement, hopefully, to say that, hey, this is a weak. So this is a weak base. You're a weak acid. So I'm going to say, hey, you know what? This is going to be a basic from its perspective. So from this perspective, it's basic. That perspective, hey, I'm acidic. And we got problems here. Because I got to figure out overall what's going on here. And the way that we're going to figure this out is the only way I can even ask you to figure it out. And that's what I had to look up really quickly, is I would have to do things such as telling you that when we look at the actual K, in this case, the K, what do I want to give you for this one? I'll give you this. The Ka for this is equal to 6.6 times 10 to negative 4. And that's the Ka of this thing right here. Right here, I'm going to tell you that the actual Ka, can I get this to you yet? I can't. I'm going to say, hold on one second, because there's something I got to show you, which I haven't showed you. And I thought I could do this one, but I can't without showing you there's an equation that you're going to need to solve in order to figure something out. So for right now, I'm going to say hold off on this. We're going to come back to it in 1 second. I will show you, so leave it in your notes. I'm going to give you the information, and you're going to have to do this really quick calculation, and then it will tell you really quickly which answer is going to be right. And I can't give it to you quite yet. That's my mistake. But at the same time, just as long as you can kind of write the hydrolysis reactions, that's all I need for right now. And then in a second, I will show you what I need to give you in order for you to ultimately figure out what's going on here. So I will do the following. And once again, that's just me looking up what the actual K and KB values are going to be. I realize we need it for this one. All right, so I'm going to jump into the notes really quickly and just go over exactly what we kind of see right here. So here we go. And also, just to point out just really quickly as well, just one more thing. In the notes, you're going to see kind of like this greened out notes that are in there. So you'll notice, even before this slide right here, before the hydrolysis notes, you're going to need this sort of stuff right here greened out. It used to be that AP required you to deal with things such as figure out the pH of polyprotic acids. Not anymore. You're only dealing with monoprotic acids. But at the same time, when you go to college, your college professor might say, hey, I want you to be able to calculate, in this case, these diprotic or polyprotic acids and what the pHs are going to be. This greened out stuff is stuff that I'm not testing you on, but I'm just giving you the notes. So when you go to college, your professor walks you through the step-by-step process. Yeah, I have it sitting there for you. All right, here we go. So if you look at it really quickly, kind of going through these notes here, we said that basically when it comes to things such as salts, that salts, of course, are going to be made up of these cations and also anions. And we got to figure out when we take the salt and subject it to water, is it going to be acidic, basic, or neutral? And of course, one of the things we want to do is kind of break it into its components, figure out what's going to happen here. If the salt actually produces the hydroxide or the hydronium cation, then I can simply say that once again, the salt is going through a hydrolysis reaction. That's all hydrolysis means, is that the cation or anion has the ability to produce either the H plus or the hydroxide. So the first example that I give you here is hydrochloric acid. And one of the things that I told you is that if we take the chloride and we dump it into water, that with the equilibrium here, that this thing cannot exist as shown because it is a strong acid, which means that there is absolutely no reaction taking place. Which means that because there's no reaction, that, hey, this salt will have no bearing, and it's just simply going to cause the solution to be net neutral. And the pH, once again, will just be 7. But at the same time, if we take something such as HF, and if I look at maybe adding a fluoride anion to it, then one of the things I can say is, hey, you are a weak base. And because you are a weak base, you can exist this way, which means I do have the ability to get the hydroxide out of this thing. Which means that I'm going to end up, once again, ultimately having a basic solution with that particular anion dissolved in water. On the next slide, this one is simply saying, hey, if we look at something like the sodium cation, then I can see that sodium cation will have an interaction with water. But the problem that we run into is, once again, we've got a strong base here. That thing would never exist this way. It would always be separated. And if it can't exist this way, then I'm going in and I'm simply saying, oh, you know what? No reaction. And that effect is going to end up being neutral in this case. Couple more problems. If you look at ammonia, this is the one that we kind of just saw. We saw that if we have something like ammonium interacting with water, it's going to once again act as an acid because it has the extra H plus there. It will deposit itself onto the water. I get my hydronium cation. I get, in this case, once again, my weak base because it is not one of those strong bases that we know of. So automatically, I don't care what base I give you, it's not strong, it's a weak base. Which means that that thing can exist, which means I get my hydronium cations, which means this solution absolutely is going to be net overall acidic based upon, in this case, the actual ammonium cation. There we go. So this is another example. Say I was to go in and say, hey, you know what? What's going on in this case with aluminum chloride? I would take the aluminum cation, interact with water, I get aluminum hydroxide. You are not a strong base in this case. Strong base, alkali metals, you're not an alkali metal. CBS, calcium, strontium, and barium. You're not that, you must be a weak base. So therefore you can kind of do this thing right here, which means that net overall, this is gonna end up causing the solution to be acidic. Now of course, I would go in and kind of figure out what's going on with the chloride. Now we already saw that the chloride would interact with water to produce, in this case, the hydrochloric acid. So I know in this case that if I look at the chloride, Cl minus, aqueous plus H2O, liquid, going to produce HCl, aqueous, plus OH minus, I can say, hey, that's no reaction because you are a strong acid in this case. All right. There we go. What we are going to do is we're just going to try a couple of these problems here. And the problems I want you to try, just really quickly. I'm going to do all of these because you got some of them for homework tonight. I'm going to go with this one here, this one, should keep that one, and we'll go with this one. Let's go with these two. Try these two. Keep in mind, for these sort of problems, typically it's like maybe a multiple choice question. They'll just say, hey, the salt was added to water. Tell me whether or not the solution happens to be acidic, basic, or neutral. And once again, it's up to the student to realize I just need to interact the cation and the anion with water and kind of figure out what the hydrolysis reaction might look like. All right, as you're going through, I'm just going to start writing the hydrolysis of the cations and the anions up here, and then we'll just talk about it really quickly. Thank you. All right, so if we look at it, first one, acidic, basic, or neutral? Acidic. Because once again, we said that over here, this is a strong acid. You are a weak base. This is definitely going to take place. So that's going to be acidic. This one we said, hey, this is no reaction, because once again, that can't exist as a unit in this case. For the next one, sodium, in this case, carbonate. If we add that to water, then we're going to end up getting what? A basic solution, aren't we? Because once again, this is a strong base. So therefore, that can't exist that way. So no reaction. Here, that's, even though it's an acid, because once again, it has the ability to go back and, hey, I'll give the H plus away. But that's not one of a set of strong acids that we know. That is going to be a weak acid. And just really quickly, say I had to go to my tables and say I needed to do a calculation with this particular weak acid. What Ka would I use for it? Would I use K1 or K2? So say I just had this weak acid. So maybe somebody dumped it in water. So ignore everything. Just saying this was going in water. So HClO, I gave you there. So 3, yes, minus plus H2O. It was going in here and said, hey, you know what, I'm gonna drop off and produce H3O plus I'm gonna give CO2 minus. Technically, that's like a typical acid reaction. The question is, would I use what Ka? Ooh. I'm asking what the value would be. But if it's diprotic, it's gonna have how many Kas? 2. So the question is it the first one or is it the second one? It's the second, because it's dropping off the second hydrogen. If you're talking about the Ka1, then the Ka1, we look at it from this perspective. So 2CO3. So this would be like a Ka2 I'd use for this. This one's a Ka1 because it's dropping off the first hydrogen in this case. Let's do a plus. Plus, I get HCO3 in this case. Minus. So just point out, I just want to make sure we're clear with the K1s and K2. For this last one that we have sitting right here, This one here, what are we dealing with in this case? Well, actually, this one here we already said was going to end up being acidic. And this last one's going to end up being what? Neutral. Absolutely. You're a strong, in this case, strong acid. That's one of the 7 strong acids I had to learn. And you are definitely a strong base because, once again, we said alkali containing things with hydroxide always soluble. And we said calcium, strontium, or barium. Yes?
Wait, sorry, for the second one, I thought it was basic.
Which one did I do? Wait a second. Ah, you're right. It's basic. I just looked up on the board. I saw acid underneath of it, but you're absolutely correct. That's basic. Because we do have the hydroxides that are sitting down here. You're 100%. Thank you for catching that. So basic solution is what we have here. All right, we got 5 minutes here. I'm going to explain in a second what your homework is going to consist of. But before I do that, I just want to show you something I think is pretty cool. I'm going to erase all this. I'm going to derive an equation here. Say I have something like this here. Say I've got NH3 plus H2O. And ammonia is a weak base. So this is a weak base. And this has nothing to do with hydrolysis. Just want to show you something. This is going to be aqueous. This is liquid. Going in equilibrium. If you're a base, well, bases do what they do. Bases accept the hydrogen cation. So you will accept it. And I will get NH4 positive. Plus, I'll get OH minus right here, aqueous. Now, if we look at this thing, for this equilibrium, would I go looking for a Ka or Kb? If I had to solve this sort of problem? Kb, right? Okay, so this is going to have some Kb value associated to it. So it's going to be equal to some Kb. Watch this here. What if I had this equilibrium? NH4 aqueous plus H2O liquid going in equilibrium. I'm going to tell you, this is a weak acid. Acids do what they're supposed to do. They're going to give away an H plus here, H plus. I'm going to end up getting, in this case now, NH3, because it gave the H plus away, aqueous. Plus, I'm going to end up giving H3O plus. Now, here comes the fun part. For this one, I would need what in order to solve this problem? K or KB? Ka, exactly. Ka. I would need its K value. Watch this. What if I wanted to do kind of like our Hess's law sort of thing going on right here? I wanted to figure out what would be the actual Ka for the two. Watch what's going to happen here. You're going to cancel. You're going to cancel. You're going to cancel. You're going to cancel. Which means that my new Ka, or my new, I'll just call it new K. We said that, hey, no matter what, it's just a product. Don't we say we just multiply these two things together, like Ka times Kb, if I want to figure out what the new equilibrium is going to be from the last test? That's what we said. We don't add them, we multiply. But look what drops down here. H2O liquid plus H2O liquid is an equilibrium produced in this case, H3O plus aqueous plus OH minus aqueous. And we're going to build on this tomorrow. Wait a second. Products over reactants. Everybody raised their coefficients. No solids, no liquid. K for this thing right here is equal to H3O plus times the OH minus. I've seen this before. What is that? KW. Which means that's what this is. We got an expression that says if you know the Ka, in this case, I know, hey, I know your Ka. And maybe there's another problem. We'll see this tomorrow. Where I'll be like, oh man, I need the KB. I don't need the Ka. You can use this expression to go to the one that you need. And let me give you this, tell you this right now. AP is notorious sometimes. They're not gonna make a whole big problem. It might be like maybe one of the last problems within that like acid problem. And they'll give you something that might look like this here. So they might give you this. And they'll be like, hey, you know what? The Ka for that is going to be here. And then you're going to have to say, you know, I'm not falling for this. I'm better than this, AP. That's a base. I can't use the Ka. But I sure can use this that's on the equation sheet and take my Ka and solve for what the Kb, which I need for this problem. Now, there will be students who will go in and they'll use, in this case, the K. You can't. Kas are for acids, Kbs are for base. We have a way in which to address this. Tonight's homework assignment is going to be pretty light, actually. So